Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a concept of energy thickness. So this energy thickness also similar to the previous two kind of thickness are there, like what we have discussed in the previous lectures. One is displacement thickness, which is denoted by delta star, and another one is momentum thickness, which is denoted by theta. And now this is energy thickness. This is denoted by delta double star. Okay, and delta is the, we know that, boundary layer thickness, which we have discussed in the first. So these are things we already have discussed. Now we are going to discuss about the delta double star, what is energy thickness. So similar to this displacement thickness and momentum thickness, the energy thickness also can be defined as like the distance measured perpendicular. You can say the distance measured perpendicular. If you have seen the previous two video lectures, we can understand similar definition. I am going to write distance measured perpendicular to the boundary, to the solid boundary, or you can say perpendicular to the boundary of the solid body, which is by that we can say the boundary should be by which the boundary should be displaced to compensate. Just I'll write shortly, boundary should be displaced. The boundary should be displaced to compensate the reduction of kinetic energy. Compensate the reduction of kinetic energy. Reduction of kinetic energy of the flowing fluid. You just have write fluid. So remaining two definitions also similar way I have written. Only the difference was there. Here I have first initially we have taken this is rate of energy or the rate of flow. Then next we have written for the momentum on behalf of this flow rate. Now we have written kinetic energy. So it depends, like for delta star it is flow rate, and similarly for the momentum thickness it is momentum. Now it is energy thickness, so we have kept this kinetic energy. So the concept I'll tell you shortly. When there is a fluid, here actually the diagram what I have taken, here actually the fluid is flowing with a uniform velocity. Here a fluid is flowing with a uniform velocity. Now I'll give an example. Suppose the fluid is flowing with a uniform velocity. So what is the flow rate will be there at this start? Suppose this is a point A and this is a point B. So the starting, what is the point, what is the rate of flow will be there? The same rate of flow you can find out from at B point also, at the B point. And what is the velocity will be there? Similar velocity, like streamline velocity will be found everywhere. And due to this, your rate of flow will be, that means there is no obstruction in this plate, in this two positions. So here actually no plate is present. There is no plate was considered for this condition. Similarly, the rate of flow is same means flow rate same means you can say the flow rate same means we can say flow rate. Suppose flow rate is same for A and B point means we can say the momentum is same. Okay, and similarly we can say kinetic energy also will be same, so there will be no loss in this. Now suppose if you keep some kind of plate in on the direction of the fluid flow, then the scenario will be slightly different. We'll get, because though there is a plate is there, so that there will be a reduction in the, or you can say there is a velocity reduction will be there in the fluid flow, because near to this wall we know that no slip condition will occur, and due to the no slip condition occurs, velocity is 0 due to the valve. And similarly, if you take this is a point A and that flow, you will get a boundary layer like this, and then the flow will be, if you take a perpendicular line, so the velocity profile will be like this. Okay, because everywhere the velocity will be not same, the velocity will be vary with respect to layer, and slowly this local velocity here, all this velocity will be small u everywhere, u1, u2, u3, u4, u5 up to u10 suppose. Now this is actually called here velocity gradient. du by dy, and that is nothing but velocity distribution also, this parabolic curve. Now similarly, so here though you are seeing the velocity is different for all these places, so obviously what was there initially at this point, how this velocity was there and what is the flow rate was there, what is the momentum of the fluid was there, so that will be not equal to at this point. Suppose this is the B point. Okay, so to find out, like if they take this point and another one condition also here, if you consider, so you can see up to here what was the velocity, what was the flow rate, and what the momentum was there. Now at this point how it is varies. So due to this plate presence, so here the plate is present. So due to the presence of the plate, there is a reduction. You can see the boundary should be displaced, compensated reduction of kinetic energy. You see, though that there is a reduction in kinetic energy, momentum, flow rate, due to that the plate what was kept here, that should be displaced. That should be displaced with a distance of some thickness, some distance need to be displaced. So that is called actually energy thickness, or you can say, suppose this is the here the plate is there. Now we should be displaced with some height. Okay, with some height it should be displaced. Now how much height need to be displaced? So that is actually delta double star. So here if you increase the height of this, then obviously the layer, boundary layer which was there, so that also be going to be increased here. Okay, so the boundary layer formation will be, if you start from here, then it will be formed like this. So how much increment happen here? Just I'll make it dark color, this one. So this position may be like this or maybe like this, and that increment we don't know how it will be formed, but we are thinking that to displace or to you see, to compensate this reduction, we supposed to displace the plate. So how much displacement is there, how much thickness is there, like to moving its plate, so that is nothing but energy thickness. Similar way what we have discussed for the momentum and displacement thickness. So to derive this equation, I'll follow the same method what we have derived previously. So initially we need to find out the mass of the fluid. So let's first consider a fluid which is flowing with a uniform velocity and that strikes the plate at the A point, and this is the A point at the edge of the plate, you can say. And let's consider another one section here, which is a distance of X point from the A point, and that we give it a B point here. Okay, up to this is the basic scenario. Now for this we can now here again at least one more point to find out these losses. Okay, to find out the reduction in the kinetic energy, first what we have taken, this is a perpendicular line, and in the velocity profile we have taken a small plate is there, a small elemental strip we have taken. You just can highlight this small elemental strip with a thickness of dy. So that small elemental strip I can draw it here. Suppose this is a small elemental strip which is the thickness of or height of dy, you can say this is, and the small elemental strip if I draw in the 3D way, so you can see like this is the construction, or this is the body object with an width of b. This is the width of the b, and this is thickness, and this is the width of the b. Similarly, if you draw in this way also, it will become like this. Okay, only you have taken this front part. Anyway, so to find out the mass flow rate, so let's we can write. So what is the elemental strip thickness is there? So thickness of the elemental strip, thickness of elemental strip, that is dy, and next u equal to, you can write this is we know that free stream velocity. This is free stream velocity, and small u equal to, I told this is local velocity. So these are the things already you discussed in the previous year also. And similarly we need to consider the x value. X is the distance, okay, and BC height is nothing but delta, that is nothing but boundary layer thickness from B to C point. This is C point divided there actually. So B to C point, the height is delta. Anyway, we will find out the mass flow rate. So write down the mass of fluid. We can write the mass of fluid, okay, flowing per second through the elemental strip, flowing per second through the elemental strip. This one we can write. We know the formula rho AV. So here we can write rho AV. So rho AV plus we can write this one rho. What is the area? Area we can see. Area is nothing but this thickness of this, and what is the width. So that is nothing but rho into u, small u, into dy into velocity. Velocity here also small u is there. Okay. So velocity not required. Okay, this one already we have written. So rho u b dy. Okay, this is b. This is actually area is b into dy, and this is velocity. This one is the local velocity, and this is density of the fluid. So these are the terms already we have discussed many times in the previous lecture also. Now this is mass of the fluid, correct? Now next we need to find out the reduction. So reduction in what? Reduction in the kinetic energy. So we know that the kinetic energy of the fluid, we can write, we know that half mv square. So kinetic energy, we can write kinetic energy of the fluid, we know that this is half mv square. So half mv square we can write. So half, this is mass flow rate. So the mass of fluid per second. So that is mass, we can write this is rho u b dy into u square. So what is the u? That is local velocity u square. Now this is in presence of plate. This one, plate is present, we can write. Plate is present. Now next things we need to write when plate is absent, or we can say the boundary layer when, let me write here, kinetic energy of this fluid, kinetic energy of this fluid in absence of boundary layer. In absence of boundary layer. So this one we can write half. Here in absence of boundary layer means the boundary layer is not there, means you can see this one, the total free stream velocity is flowing here. Okay, so you can write mass flow rate will be there. So this plate is not there, means in this region, or you can say though this plate is never there, boundary layer is not there. Boundary layer is not there means which velocity will be going to strike in this? So obviously the velocity u is going to strike this elemental strip. So what is the mass of this fluid? We can see already we have written, that is rho u b dy, and the velocity is going to change, that is free stream velocity, because boundary layer is not there. So boundary layer not there means the free stream velocity can strike that one. Now next we need to find out what is the loss of kinetic energy. Loss of kinetic energy through the elemental strip. Through elemental strip. Through elemental strip. Now loss of kinetic energy through elemental strip, what we can write here, like without boundary layer what was the kinetic energy, and with the boundary layer what was the kinetic energy. If you minus that one, then we can get it. That means we can write half rho u b dy into u square minus half, same thing, rho, and here it is u b dy, okay, and this is u square. Okay, now if you just take a common up from this, we can write this is half rho ub, we can take common, bracket start, capital U square minus small u square, bracket close, into dy. So the total, now this is, we can give an equation actually. So this is, let's give equation 4, and this is equation 1, this is equation 2, and this one we can give equation 3. Now this is equation 4. Now this is the loss of kinetic energy through the elemental strip. Only the small part what we have considered, through this much losses are there. Now we need to see from this total boundary from here to B to C point, so how much losses was there throughout this total object. Now for the total losses, to find out the total loss of, you can see the total loss of kinetic energy, okay, kinetic energy of fluid passing through, you can see passing through BC. Passing through BC, we can write, just we can integrate this one actually. So integration of 0 to delta, because I told you BC, the length is total, delta is there. So passing through BC, we can write the equation like half into rho into u into b, and this is bracket started, and u square minus small u square, and this is dy. Now again we can write this is 1 by rho b, let 1 by rho b, and 0 to delta. U is, we can, u part we can take it to inside, u square minus small u square and dy. Now rho you can take constant when, now when the density is compressible fluid is there, incompressible fluid, then you can take rho is constant. Okay, so this is up to that you can understand, and here you can give an equation also. So this one also we can give equation 5. Okay, now the next part we need to see what is the reduction, or what is the distance that is traveled by this, or we need to compensate the reduction what we are going to take. So let's consider the delta double dash. So I told you delta double dash is the distance which is going to be traveled to compensate that. So distance by which the plate is displaced, distance the plate is displaced, distance the plate is displaced to compensate the reduction of kinetic energy. This one we can write, compensate the reduction in kinetic energy. Okay, now so we can write the loss of kinetic energy again, loss of kinetic energy through delta double star, what we can write with a flowing velocity u, with a flowing velocity u. Why this free stream velocity need to be considered? Because when there will be bound, see, when we are displacing this distance or plate we are displacing, so obviously we'll get the free stream velocity at this region. That means above to this boundary layer we are getting free stream velocity. So the free stream velocity is going to strike this plate. So the loss of energy or loss of kinetic energy through this one flowing through the velocity of u, we can write again same thing. This is also, what is the kinetic energy? Half mv square, half mv square. So here also we can write half into rho, half into rho into v into v square. So here we can write this is half rho area we can write this is b, width, and the thickness is now delta star. Initially the thickness what we have taken, that is dy, now it is delta star into free stream velocity u, and this is u square. Okay, now if you can write this u equal to, sorry, not u equal to, this is the loss of kinetic energy through delta star. This is, we can write half into rho into b delta double star, and this is u square into u, this is uq. So this one we can give equation 6. I hope the previous what we have given, yeah, 5 given, now 6. Similarly we need to find out this, you equate this equation loss of kinetic energy with the plate and through this delta star. So you can equate these two equation. Now equate the two equation of 5 and 6. What we can write here, this one we can write half into rho into b delta star into uq, and previously we got the equation that is nothing but half into rho b we have taken outside, and this is integration we have given 0 to delta, then what we have written u into capital U square minus small u square, and this is dy. Now we can cancel, see, half rho b, everything can be cancelled. Now directly we can write this is delta double star, and this uq take it to this side, so we can write this is 1 by uq integration 0 to delta, and this is u capital U square minus small u square dy. Now this let's take this inside, so we'll get here directly, I'll write this delta double star, and this 1 by eq I'm taking to inside this integration. So what we'll get here directly 0 to delta, and this is small u by capital U. Let me write here 0 to delta, and this is u by capital U, uq, u minus u square minus small u square dy. Okay, now what we'll get here, this one 1 minus u square by capital U square bracket close, and this is dy. This is our final equation. This is for the energy thickness. Okay, so for the previous equation what we got, their square was not there, here square is there. Now see what I have taken, I just taken this eq inside to this one. Then after that what I'll do here, u square by uq minus u square by uq. So what I'll do here, I'll take just u is outside, u is outside here. This is integration 0 to delta, all the things is there. Now what I'll do, I'll take a common of u square from here. Okay, or just I'll take only u. If I take u common outside, like next step what will be there, u by u, then what u square is there. So u square will be cancelled, and this u square by capital U square. So this is the final equation of the energy thickness. So I hope you understand this concept of this energy thickness and how it is derived and what is the concept of this. Only the thing is all these three thicknesses are same. Only if you need to remember this definition, only you need to change that flow rate and momentum and kinetic energy. Remaining all things are same. So if you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you.